In this video, we will talk about second-order differential equations. To fully understand this video, knowledge in differential and integral calculus, as well as complex numbers, is required. Differential equations are equations that contain derivatives, whose general solution is given by all functions that satisfy the equation. Differential equations appear everywhere in physics. There are different types of differential equations. ODEs, or ordinary differential equations, are equations that possess only one independent variable. Therefore, there are no partial differentials. The simple harmonic motion equation is an ODE, but the wave equation isn't, as there are partial derivatives for time and position. There are also linear ODEs, which include the dependent variable to the first power at most. The SHM, again, is a good example for this, but an equation such as dy over dx plus xy squared equals 0 is not linear, as y squared appears. Finally, an homogeneous ODE is a linear ODE in which the dependent variable appears to the first power in every term. The simple harmonic motion equation is homogeneous as x of t appears in every term, but this equation isn't, as the right-hand side does not depend on y.
How to solve a homogeneous ODE? First, let's consider a homogeneous ODE of the general form, which can be solved by y is equal to e to the power of k times x. By differentiating y with respect to x, we get k times e to the power of k times x, and by doing so once again, we get k squared times e to the power of k times x. Substituting those into the original equation, we get the following. And by dividing both sides by e to the power of k times x, we get the following quadratic equation. Dependently on the values of p and q, we need to consider two cases. Firstly, when the determinant is non-zero, we get two solutions, k1 and k2. And the general solution of the original equation is given by the following function. On the other hand, when the determinant is 0, k is equal to minus p over 2, and the general solution of the original equation is the following function.
So the full general solution of the ODE is a sum of the complementary function and something called the particular integral. To find the particular integral, you'll essentially use trial and error. Here, depending on what fx is, will depend on what you trial. Once you've decided what you will trial, you will then differentiate it and substitute it back into the original ODE. For example, if f of x is a constant, we just trial another constant. If it's a constant times x, we trial lambda plus mu x, and so on for increasing polynomials. If it's a combination, then you choose the highest order corresponding to the trial. For example, here it's x squared. If f of x is in the form of an exponential, we then trial another exponential to the same power, again using a constant in front. However, there is an exception in this case, and if s is a root from the complementary function, then you trial lambda x e to the x instead. For any trigonometric function, you trial this equation with the omega x contained in the brackets the same as that of the f of x. So for a quick example, find the particular integral, we have this ODE, and since the highest order of x on the right hand side is 1, we will trial y equals lambda plus mu x. We then differentiate this function to give these two, and putting those at the top there, we can then substitute it back into the ODE, which can give us this. Expanding these brackets and collecting the coefficients can give us these expressions after we equate them, and you can solve them simultaneously to find the coefficients. You then put them back into your particular integral, and this added to your complementary function is your full general solution.
So just to recap, in this video we showed how to solve second-order differential equation. The first one was homogeneous, where y and all of its derivatives occur to only first power. We know that the function that can solve this equation can be written in the form e to the kx. When this function is differentiated and plugged back into the differential equation, it will return us a quadratic equation in the form Now, when we have our quadratic equation, we can solve for k, and two things can happen. If we get two expressions for k, which can be either real or complex, the general solution to the differential equation will be in the following form, where a and b are arbitrary constant. In the second case, where k will be only single valued, because the solution to the differential equation will be in a slightly different form. When solving a homogeneous differential equation, the general solution will have two parts. First, the complementary function in the form e to the k1x plus e to the k2x, which would be a general solution to homogeneous equation. Second part of the solution is strictly dependent on the function of f of x. According to what the function f of x is, we choose a suitable trial function, which then we differentiate and plug into the differential equation and solve for individual components.